Hi everybody, welcome to Chapter 5, Probability Distributions, Section 5.5 on a special type of probability distribution known as a Poisson distribution. The key concept in this section is that the Poisson distribution is another discrete probability distribution, which is important because it's often used for describing the behavior of rare events, so events with very small probabilities. So the Poisson distribution is a discrete probability distribution that applies to occurrences of some event over a specified interval. The random variable x is the number of occurrences of the event in an interval, and the interval is usually time, distance, area, volume, but most frequently it's time, as we're going to see. And the formula for this is given here. So your probability of x is going to be equal to your mean raised to the power of x multiplied by e, I'll explain what that is momentarily, raised to the negative mean, all divided by x factorial. And here, e is actually a given, it's a standard. So it's kind of like pi. It's a mathematical constant. So whenever you see e, you actually just plug in the number 2.71828. And here it's important to point out that your mean is going to be given by the number of occurrences of the event over the interval of time, as we're going to say. Okay, so some requirements for a Poisson distribution. The random variable x is the number of occurrences of an event over some interval, like I said, typically time. The occurrences have to be random, meaning that they're not somehow provoked or any of those things. The occurrences have to be independent of one another, so they don't impact one another. And the occurrences have to be uniformly distributed over the interval. And again, the mean is given by this symbol here, our mu, and the standard deviation here is actually equal to the square root of your mean. So this is another way of calculating out a mean and a standard deviation that is specific for the Poisson distribution. So some differences from a binomial, which we just talked about. So the Poisson actually differs from the binomial in a couple of ways. The binomial distribution is affected by the sample size and the probability of success, lowercase p, where the Poisson distribution is only affected by the mean. If you look back at the equation, you'll see why. In a binomial distribution, the possible values of the random variable x are 0, 1, blah, 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 up to whatever your n is, the maximum number of trials that you had. But in a Poisson distribution, the possible values of x don't have the upper limit because they are not limited by the sample size n, because again, n doesn't factor into the equation for binomials. So let's do an example. For a recent period of 100 years, there were 530 Atlantic hurricanes. We're going to assume that we can use the Poisson distribution model, and we want to find the mean number of hurricanes per year, and we want to find the probability of x. If the probability of x is the probability of x hurricanes in a randomly selected year, we're going to find the probability of getting 2 hurricanes in a randomly selected year. So let's see how we calculate this. So to find the mean number of hurricanes, we're going to take the number of hurricanes that occurred over the interval of time. So there were 530 hurricanes that occurred over 100 years, which is 5.3 hurricanes per year, roughly. So if the probability of x is the probability of x hurricanes in a randomly selected year, we want to find the probability of 2 hurricanes. So using our equation, and the mean that we've already calculated, we're going to plug everything in. So again, it's our mean raised to the x power, so 5.3 raised to the power of 2, which is the number of hurricanes we're interested in, multiplied by e, which is our constant, 2.71828, raised to the negative mean, our mean was 5.3, so negative 5.3, all divided by x, which is 2, factorial. And when you do out that math, you get 0.0701, which is 7.01%. So again, this can be very helpful, these types of equations, when it applies to an interval of time. And you'll be able to recognize them as well as in the actual problem itself. The problem will tell you whether it's a Poisson distribution or not. This slide, please don't worry about this too much. This is that you can use the Poisson to approximate binomials at times, but we're not really going to spend a lot of time on that. So please don't spend much time on that or this last example that's here. And that ends section 5.5 and actually all of the content for chapter 5.